So now we're going to focus on actually finding distances between points, planes, and lines. It's like lion, tigers, and bears. Oh my. There are 6 different ones to kind of look at. You got the point to point, point to plane, point to line, plane to plane, plane to line, and line to plane. So there's 6 different options. The blue option, point to point, you already know how to do that. That's the distance formula in 3D. It's like finding magnitude of a vector, that sort of thing. You've done that many times. Okay. And then 4 and 6, they don't make sense all the time. They would only make sense if they are parallel, then there is one set distance. But imagine if I had, think of that as 2 lines, or if you pop it out and it's coming right at you, those are 2 planes. What distance are you asking for if I ask you find the distance between them, find the minimum distance? Well, the minimum distance, if they intersect, would be 0, because they intersect there, okay? But that distance would always be changing further and further out. So that one doesn't make sense unless you talk about them being parallel. Because then if I have a parallel plane and a parallel plane, you can actually find the set distance, okay? 2, 3, and 5 are more specific because it's kind of a mixture of things, okay? So let's look at some of these. First one is we're going to find the distance between a point and a plane, okay? The idea of this in my mind is imagine being in a tree house and you want to drop a rope down to the ground, okay? And you want to know how long of a rope do you need to drop it straight down to the ground. And then now obviously this tree house and this rope and all this in 3D world, these planes are not always flat on the ground. They're not always the XY plane. They're always tilted a little bit. So we're now looking at a tree house being tilted with that. This is what the book gives you. And again, through this year, you're going to see a lot of times they talk about the magnitude of the projection, and that's where I define it as the component. Remember, there's 2 types of projections. There's a vector projection and a scalar projection, okay? So we're going to focus on the scalar because I'm asking for a distance. So what I'm going to do is we have the plane, we have our point. So this Q is kind of my tree house, and I want to find the distance of the rope. So this green would be what I'm considering the rope, okay? Now notice that green is the same as right there, okay? So it's how much of PQ, how much of this vector falls down, how much of it falls down on the normal, creating that distance, okay? So with that, if you remember, let me see if I can draw this a little bit again. Let's say I have PQ, and I'm giving you the normal, and I want to have this fall down, and I write this as the component of PQ on N. Remember, the component is the scalar projection. Okay? So how much of it is on it? That would be my distance. My distance is the component N, component of PQ on N. Well, to get that distance, it's nice to have an angle. Okay? So think geometry again. This is kind of me reminding you of how to get the component. Geometry again, you could say cosine of theta is adjacent, which is component of PQ on N, all over PQ. Now I don't want to say PQ because then this would be saying an angle is a scalar component all over a vector. But if I magnetize it, or give the magnitude, now I have a length over a length, and that helps me give the angle. Well, if I want the distance is the component, you could say component PQ on N is PQ magnitude times cosine of theta. Okay? Now, cosine of theta can be brought down as PQ. Cosine of theta would be PQ dot N all over the magnitude of PQ over the magnitude of N. And this, again, would be the component. Well, what cancels? The magnitudes of both the PQs go away. And you're going to say the distance between a point and plane is the component of PQ on N, which is PQ dot N over the magnitude of N. Okay? So, we're going to be using that on this next problem to try to see if we can find out how long that rope actually is. Okay? So, this first question says, find the distance between the point Q, 3, 2, 1, and the plane given by that. Okay? I know Calc 3, and I always draw a picture to help me remind myself of how to do this. So the way I draw the picture, there's my plane. Out of the plane is my normal. And that's given by the coefficients of the plane. So it's 1, negative 1, 2. Okay? I put Q over here. It's point Q, which is 3, 2, 1. Now notice on that last page, I kept telling you I needed a PQ. I needed a PQ. So the whole thing here is I need a point on the plane. Any point will work. It does not matter at all what point you put, as long as it's on the plane. So in looking at this, I might use the point 0, 0, 2. What did I do? I found the z-intercept by hiding the x and y. So I had 2z equals 4, so z equals 2. Could I have used 1, 0, 0? Yes. Could I have used 0, or not 1, 0, 0, sorry, 4, 0, 0? Yes. Or you could have used 0, negative 4, 0. It does not matter which point you use. You just got to pick any point out. So I'm going to do the 0, 0, 2, and I'm going to call that my P, and that is 0, 0, 2. And with that, then, I have enough to get my PQ. So my PQ vector would be 3, 2, negative 1. Okay? So now, my distance, if I'm trying to find distance, remember, would be my dropping from, I don't have any more colors, so I'll just go back to, I'll go back to green here. This is the distance I want, which is the same as that, which is the component. So my distance equals component PQ on N, which is, we had it as PQ dot N all over the magnitude of N. Okay? So PQ dot N, 3 times, so that's 3 minus 2 minus 2. The absolute value of that, all over the magnitude of N, which is 1, 2, square root of 6, which is 1 over square root of 6. That's my distance. Okay? I like drawing the picture because it helps me figure out what things I need. I needed a point P, and any one of those points would have worked. I just happened to use this point. And with that picture, it helps just kind of help me orient why the formula is what it is. Okay? Now, the question I like to ask on top of it is this. Key question. What is the closest point on a plane to a point off of the plane? So this question is asking, now find the closest point on the plane to the point Q. You see it. I can show you where it is. I want this point. So when you drop the rope down from the treehouse, I want to know exactly where it lands. So if you drop it perpendicular, it's going to fall. I want to know the smiley face. So that's the guy I'm trying to find, is that. Okay? Now there's two ways to do this. One way might feel like a little bit more math involved, but it gets you the answer right away. The other way might feel quicker, but then you need to do a check on it. Okay, so I'm going to show you both ways on how to get it, but your preference on how to get it. So my whole goal is to find the smiley face. Okay, so I can kind of tell you what we're doing. We're going to start at point Q, which is 3, 2, 1. And I need to move. So I need to move, what's that distance again? I need to move the distance 1 over square root of 6 down the vector n, which is 1, -1, 2. Now, the key to all of this, why it can be a little bit tricky, is the phrase down. Okay? From the picture that I drew, we know what down means. I'm going down it from, like gravity, from up top on the treehouse down to the plane. But when I say down, it's a little bit harder knowing, is 1, -1, 2. Is the normal vector right now, is that moving up or is that moving down in general? And it's really hard to see it with the orientation because these planes are slanted. Is the point really above the plane or below the plane? Well, I will always draw it above the plane, so I will always say the word down. Well, what does down mean in terms of moving with the vector? Okay? So, to do this, I want us to think about lines again. And lines, like that last slide, you need a point and direction. Do we have both of those for a line? Yeah. We already have the point, 3, 2, 1, and we have this direction, 1, -1, 2. So I can give you an equation of the rope line. I can tell you x is 3 plus 1t, y is 2 minus t, and z is 1 plus 2t. That is an equation of the rope line. And I know what the plane is. So if I have that, I can plug these components into the equation of the plane. Okay? So I'm going to take these guys and throw them in the equation of the plane. And that plane again was x minus y plus 2z is 4. So x minus y plus 2z equals 4. So I have 3 plus t minus 2 minus t plus 2, 1 plus 2t's equal 4. And I'm going to solve for the parameter t. So let's see here. When I do that, I'm going to get 3 plus 6t equals 4. So then 6t equals 1 and t equals 1/6. That's the time parameter that tells me how long I need to walk down that line. Again, I use the word down lightly, quote unquote down. So 1/6 the way down that line will give me that time component. So what I can do is go, okay, so now I know that by plugging t back into my rope line, I will land on the smiley face. Okay? So by doing that, I can say x equals 3 plus 1/6, which is 19/6. Y equals 2 minus 1/6, which is 11/6. And z equals 1 plus 2 times 1/6, which is 1/3, which is 4/3. And I now have the point and this is the smiley face. This is where the rope would land on the ground. So if I drop the rope from the treehouse, it would land on the ground right there. Okay? Now, that is one way to do it. This way it might feel like there's a little bit more algebra involved. I used the rope line. I plugged it into the plane. You know, it's kind of like substitution. I'm trying to find an intersection, so I connect the rope line to the plane by substituting in. I solve for the time parameter, and I plug that time parameter back into my line to figure out where my point is. Okay? There's another way to do it. So the other way, way 2, to find the smiley face. Okay? Way 2 is this. You already know the point. So I have 3, 2, 1. There's my point. I already have my direction, which is 1, -1, 2. And I need to move in that direction, but I need to move how far? The distance I want to move is this. So here's my distance. So I have a point, I have a distance, I want to move in that specific direction. Now, right now, if I move 1 square root of 6 in that direction, I did not move 1 square root of 6 because I have not unitized the direction. So if you unitize the direction, you'd be doing the magnitude of 1, -1, 2. So now I have a point, and I want to move 1 square root of 6 in that unitized direction. Now the whole key here, though, is I want to move. This is the moving down part. And this is what the issue is when I say down, did that mean up or did that mean down? Did that mean positive or did that mean negative? It's hard because we don't know how we orient it. So let's just look at the plus way versus the minus way. Plus, to me, that would feel like the word up, and minus would feel like the word down. Does that mean it's always that case? No. Okay? But let's see what I would get. The plus way would be 3, 2, 1 plus 1 over square root of 6 in the direction of 1, -1, 2 unitized, which is square root of 6. So now this is 3, 2, 1 plus 1/6, 1, -1, 2. Now that 1/6 should look very familiar with the time parameter. Okay? If I do that, I go with, this is You just add specific values. So 3 plus 1/6 of this direction gives me 3 plus 1/6, 19/6. 2 minus that is 11/6. And 1 plus that is 4/3. Is that the correct answer? Yes. Look what happens when we do the down. 3, 2, 1. Minus 1 square root of 6, 1, negative 1, 2, square root of 6, 3, 2, 1, minus 1/6, 1, negative 1, 2. And this one actually gets me, let's see, 17/6, 13/6, and 1/3. Okay, so the correct answer is this one, and this was by me moving up, where this one was moving what we kind of would consider down, but it's not there. So the reason I know this one's right is because I already did it the other way. But the way you could do it is you could do this way. You could do way 2 and get your 2 answers, and to check, plug in both versions into the equation of the plane. Whatever one works is the actual point. So plugging in that red version there works, so that would be the point. Okay? I really like this concept. I'll highlight what I mean by the concept. This is super important for you guys to know. Point plus distance times direction unitized can move you. Okay? That is so important. The whole thing, though, is be very cautious of how you're moving. When I say positive, that does not mean up always. When I say negative, it does not mean down always. Okay? So this one, you can get 2 points really quickly. You just need to make sure you know which point works by plugging into the plane. Where this one might seem like a little bit more math, maybe, but it follows the logic a lot cleaner. You have a line, you have a plane, you find the intersection by setting them, or not, by substitution. Once you find the t, you can plug it back in, and you guarantee have the correct version. Okay? Either way is fine by me.